in the field, actually you don't have to be in the field, you just have to drive next to any highway where they have the right of way also of the transmission line. Try to find me a transmission line that where the wires or the conductors are hanging in an equilateral triangle. You'll find none. What you will find is this configuration, which is the H type, right? So they have that track. So now he has one distance, capital D, and that distance is capital D, and this whole thing is 2D, right? Now he says, if I look at the voltage drop on phase A and phase B and for phase C, I will find that the voltage drop is not the same. The two guys on the outside will have a drop that's identical to each other, but the fellow in the middle has a different voltage drop, linear, okay? So what did they come up with? Transposition of lines, right? Transposition, if you remember it, you know, you go A, then goes down B, goes down C, and so on. Assume it's transposed, which is a Stone Age technology, but they still do it, right? Then they define a thing that they call the geometric mean distance. So they replace this D here by the geometric mean distance. I'm getting there. And they divide it by the geometric mean radius. Because that allows them to go, so why was I doing that? Why was I saying that? Because the question was, how do you handle a specific configuration in the cable itself? See, we were having this D over little e, right? That's how it started. So you looked at it and you say, well, this is very simple, okay? And all I tell you is that, yes, people that knew how to handle this situation using some magic, what is the magic? Is to reduce things to something that we can use as the geometric mean distance and the geometric mean radius. The geometric mean distance is simply that you take all distances between the conductors, multiply them together. So if you multiply 6 of them, you take the 1/6 root. And that would be the geometric, that's why they call it geometric mean distance. Because it's a geometrical mean. And it was algebraic mean, then you add them, you divide by the number, right? Okay. Do you have bundle conductor lines here in Malaysia? What is the highest voltage that you get? 345? 380?
275.
What?
400 kV.
400 kV? Okay. So if you have 400 kV, 500, well, same answer. I mean, for me, I would say that you are using bundle conductor lines. Okay? Now, the bundle conductors, if you have a three bundle conductors to the phase, then you have that. So the engineer is not going to waste his time, although if we had the computers in the 1930s, the history of the world would have been different. The history of technology would be different because we wouldn't have these weapons. My short answer is that he's going to get an equivalent G on the top and an equivalent D on the bottom if he wants to do the calculations. Actually, it's not doing the calculations, I beg your pardon. It's to have a handle to understand what is happening. Let me just restate what I said. If you have, when you have this situation, that's three bundles, three conductor bundles, 1, 2, 3. How many conductors do we have now? 9. Okay. Well, your life is going to be more complicated because we're going to take the neutron down. Why do I say beautiful? It's because you stretch them out and you write one row for the voltage drop on this conductor and the effect of this on him, this on him, this on him, this on him. And so you go, okay, so you have one row, 9 elements. And then the next row, and next, and next. So you end up with a 9 by 9 matrix. Now, Laurie Snyder told us in 1975, he stood in a conference and he attacked everybody. He said, when I graduated, I went to look at motors and generators, and I could not find the matrices. Of course, he was just making fun, of the academy, people that look at it and say, it's a 9 by 9 matrix. Now, why would he make fun of those people? It's because, yes, if I want to do the calculations using computers, fine. But if I wanted to make a decision as to increase the distance or decrease the distance, or whatever the answer will be, you have to have simpler rules. Okay? And to remind you of what they do, when they are looking at the machines, so what am I doing now? The machine is running, and they give us this crazy statement. Let's say that there is a short circuit on the terminals of the generator, right? And they will say that because I have damper windings and so on, then the current will be oscillating, right? But there will be decaying. But because nobody is going to listen to anybody, especially if I don't know what I'm talking about, right? And says, go ye out forth and draw this and then make conclusions. Right? They say, don't bother me with that. I'll take the envelope and I'll approximate things like that. And if he was German, he would say, Jawohl, Herr General, because he understands now that what they have done is not to take waves and all kinds of e to the minus t and stuff like that, but represented things with a subtransient and a transient and a steady state reactance. Okay, so how many of us remember in our past that somebody said to discuss the oscillations between machines we have to understand where these reactances are coming from. And it turns out that these were genius people. They were amazing in the first half of the 20th century. They didn't have, the General Electric had a computational lab. It had 120 humans sitting with a crank calculator doing parallel processing. Right? You ever heard of that?
No.
The calculations that they used to do back in the 1940s to the 1960s, if you ever have the good fortune to go to the Computer Museum in Palo Alto, right? You see all of these pictures, okay? So because, I wasn't there, but there were people who were 90 years old going on that tour of subjects. But in any event, all I'm trying to say is that because they did not have the computational capabilities to handle the large size problems, right? Then they resorted to tricks and approximations that they can talk to each other about, okay? So where is the origin of that? See, I took advantage of your question, right? Took advantage of your question by taking you around the world and then come back to the answer that could have been done in 2 seconds. He's going to find a formula to fill for an equivalent. This is what I said at the beginning, right? An equivalent of that capital D and an equivalent of that little d. Because you were arguing with me, about why he did that, right? I say, okay, let me say something else about cables and life in general. Now, I'm trying to restrain myself from drawing some caricature here, so you can imagine any picture you want. So we have got 3 cores in there, 3 conductors, right, inside. And someone said when they were dealing with adjustable speed drives and then variable frequency drives, that we need to create a filter, a capacitor. Now that guy, whoever it is a genius. Either that or whatever he was eating, I'd like some of it. Because he says, I will put 2 additional dummy conductors inside the cable. And I'm not so sure whether it was Allen Bradley's or Rockwell, one of the 2. And they just put an additional conductor inside. And now what happened is that he modified the capacitance profile. It doesn't matter, whether I can derive that or not. The fact of the matter is, as soon as I put this conductor in here,